Hi everybody, welcome to the very last video of the semester, where I'll be going through problems from chapter 13.1, 14.1, and 14.2, so the week 6 problem set. So I'll be going through some problems from this, so we're dealing with trees, planarity, and graph colorings. Congratulations, you made it to the end. Hopefully this will help you with the exam, and then you'll be all done. Very exciting, very exciting. All right, let's start here in section 13.1 with problem number 4. In this problem, we're asked to, so a lot of words to say. I'll tell you what this means in a second. So we want to take K6, and we want to find 3 spanning trees so that the edge sets of the trees partition the edge set of K6. So we don't want to use an edge more than once, and we want to use every edge exactly once in these 3 trees. And the degrees of each tree are 3, 3, 1, 1, 1, 1. So what this really is, this is called the decomposition of a graph. Whenever you can take a graph, decompose its edges into smaller graphs so that those edge sets of the smaller graphs partition the edge set of the original graph, we call that a decomposition. So here we're decomposing K6 into 3 trees with this degree sequence. So this is really, once you understand the question, it's really just about kind of trial and error, just trying some things. I tried one before I got it, but what I'll do here is I'll use red for T1, blue for T2, and green for T3. So what we're really doing here is we're coloring the edges of K6 so that each color class, each graph of each color, is a tree with this degree sequence. So let me see if I can remember how I did this. So I know I want these 2 vertices of degree 3. I'm going to put them opposite of each other. And again, to get to the solution, just keep trying things. Eventually you're going to get it. Trust me on that one. Eventually you're going to get it. If you keep trying things, your brain's going to find a solution. So I'm going to draw across from each other, and I want these both to be degree 3. There's actually another related concept in graph theory called graceful colorings. So a different kind of coloring, or rather a graceful labeling of a graph that's relevant to this. So if you're interested, look up graceful labelings of graphs. It's a very popular research topic with some really interesting unanswered questions in it. But as far as we know, every tree is graceful. We don't know that for sure, but every small tree is graceful. And because it's graceful, we can decompose certain complete graphs into trees. But that's beside the point. So there's my red subgraph, and then I'm gonna do this cyclically. So this is something called a cyclic decomposition, which means I'm going to take that red subgraph and I'm just going to rotate everything just shift everything 1 vertex with a rotation. So my T2 is going to go here, and that would go there, and that would go there, and then this would go here and here. And then I'm going to rotate again. So now my long edge is going to go there. This will be adjacent to that one, this will be adjacent to that one, and this will be adjacent to that one, and this will be adjacent to that one. So notice now I have every edge of K6 accounted for. It's either green, blue, or red. I'm not missing any edges. And that each subgraph, each color class here of the edges is a tree with this degree sequence. So this works. Just really, the only tools we have to do this is you just got to try things, try, and eventually you should get it. But there's one possible solution. All right, number 10. We have a tree with 22 leaves, 4 vertices of degree 4, 3 vertices of degree 6, and exactly 2 vertices of degree x. What is x? So with a tree, we know that. So if we have a tree of order n and size m, by the way, there's another formula specific to trees that's like the first theorem of graph theory that you could use here. I'm not going to use that one. I'm just going to go back to the first theorem of graph theory because I know and love it. But if you're interested, you could try theorem 13.12. you might take a look at that and see if you can solve this problem using that theorem. But we know that the size of any tree is 1 less than the order of the graph of the tree. So if we can figure out the order, we know what these all have to sum up to. So it has 22 leaves. So here I'm going to calculate the order of t. Let's see, we have 22 leaves. We have 4 vertices of degree 4. We have 3 vertices of degree 6, and 2 vertices of some degree x. And that's it. And so the order here is 26, 29, so order 31, which means we know our size. Since this is a tree, our size is 30, which means the sum of the degrees, by the first theorem of graph theory, the sum of the degrees in the tree must add up to 60. So we have 60 equal to, so the 22 leaves, those all have degree 1, so we would just get 22 times 1, or 22, plus 4 times 4, 16, plus 3 times 6, 18, plus 2 vertices of degree x, 2x. So 60, that's 38, so 56, plus 2x. So it looks like 4 equals 2x, which tells us x equals 2. So we have exactly 2 vertices of degree 2 in the tree. There we go. So remember, first theorem of graph theory is super helpful, super helpful. All right, let's jump over to number 16. Again, we're given some information about degrees of vertices, except this time it's a little bit more difficult. So we have 3 vertices of degree 4, 5 vertices of degree 6. Remaining have degree 1 or degree 3. So right off the bat, I'm going to let x be the number of vertices of degree 1. So that is the leaves. And let y be number of vertices of degree 3. Those are my 2 unknowns, and we'll see what relates these 2 variables. There are 3 times as many n vertices, leaves, vertices of degree 1, as degree 3 vertices. So if I know the number of degree 3 vertices, then 3 times that is the number of n vertices. So that is x equals 3y. So I have that relation. Do I know the order of this graph? Let's just put together as much information as we can. So n, the order, the number of vertices. So let's just add up what we can. We have 3 vertices of degree 4. We have 5 vertices of degree 6. Then we have vertices of degree 1 or 3. So that's x plus y. So that's telling me n is 8 plus x plus y. So if I know x and y, I can figure out the order. And that's really the end goal here. We want to know the order. So in order to figure that out, we're going to need to know x and y. Okay, and once we have the order, I mean, we have it expressed in terms of x and y, we can write the size of the graph, right? The size is 1 less than that. So what this is telling us is that m is n minus 1, which will be 7 plus x plus y, which is also, remember, twice that is the degree sum. So let's go ahead and use the first theorem of graph theory. Notice we have this equation relating x and y. We have this equation relating x and y. And then we'll have a third equation relating x and y when we compute the degree sum. So twice the number of edges. So in this case, that'll be 2 times 7 plus x plus y. So 14 plus 2x plus 2y is the degree sum. And so that would be what? We have 3 vertices of degree 4, so that's 12. We have 5 vertices of degree 6, so that's 30, plus x vertices of degree 1, so plus x, plus y vertices of degree 3, so that's 3y. So here is my third equation now relating the variables x and y. So I have 3 variables. Notice I have 3 unknowns, hence we can solve this. And in fact here, now that I've already used this one to do my degree sum, I have 2 variables with x and y, and so I should be able to solve this system of equations. So I'm going to take that x equals 3y and substitute it into this equation everywhere I see an x. So this is going to be 14 plus 6y plus 2y equals, I'll simplify that, 42 plus 6y. So it looks like those y's cancel out. I have 2y equal 42 minus 14, which is what, 28. So if 2y equals 28, so y equals 14. So if y equals 14, then x is 3 times that, so x is 42. And hence my order then is n equals 8 plus 42 plus 14, that's 56, 64. So n equals 64. This tree has 64 vertices. So you might also, you could try theorem 13.12 on this one. I bet there's a way to do it using that. But I just like to come back to the fundamentals, just using the first theorem of graph theory, writing down all the information I have, remembering how it relates, and then putting these things all together, solving a system of equations. So that's how I like to do these ones. All right, graph G has order n greater than or equal to 3 and size m equals 3n minus 6. Which are true? Is G planar? Is G non-planar? Or is it impossible to tell? So remember, this is one of the most important theorems in 14.1. So dealing with planar graphs is that if we know that the size of a graph is strictly bigger than 3n minus 6, then G is non-planar. So we need it to be strictly greater than 3n minus 6, and then we know for sure it's non-planar. There's just too many edges to untangle it. Of course, if m is less than or equal to 3n minus 6, it doesn't guarantee the graph is planar or not. We can't say that. And so here we have m equals 3n minus 6, so it's not strictly bigger than 3n minus 6, and so we don't know if it's planar or not. So my hunch is that it's impossible to tell. We certainly can't say it's non-planar without more information. We can't say it's planar without more information. So to just illustrate this is the answer, and we can pretty much conclude that from what we just talked about. It doesn't satisfy the hypothesis of this, and we don't have any more information to conclude if it's planar or not. But just to illustrate this, I want to do like I did in the last video. If it's impossible to tell, then I should be able to find two graphs with this condition, that one is planar and one is not planar. And so that's what I'd like to show you here. So notice, if I let n be 4, and I make the complete graph on 4 vertices, I'm going to draw it like this. It's planar. It's planar drawing, or planar embedding. Then n is 4, m is 6, and what's 3n minus 6? That's n is 4, so this is 6. So we do have m equal to 3n minus 6 here, and this is certainly planar. Look, I drew it as I have a planar embedding of it, so clearly it's planar. K4 is planar. But then I'll also show you another one with the same degree condition, the same size order condition, that's not planar, thereby demonstrating that it is absolutely impossible to tell without more information. So I know that this is how I came up with it. I'll explain to you how I came up with this graph. I know that K5 is non-planar. So what I'm going to do is I'm going to make K5. This is one of these two special graphs that we know is non-planar, and that every graph that's non-planar either contains this is a subgraph, or a subdivision of this is a subgraph, or K33. K33 is the other special one that's non-planar like that. So I know this one's non-planar, and I also know that if I subdivide an edge, that's not going to change whether it's planar or not. So right now we have 5 vertices and 10 edges. So if I subdivide this edge, I'm going to put a vertex there on that edge. That'll bump the number of edges up to 11, and the number of vertices up to 6. I'm not quite where I want to be. I'm going to add one more edge in, And again, adding an edge in isn't going to suddenly make this planar, right? I added more edges. How could that possibly make it planar? It can't. And so now, if you count the number of vertices, n is 6, and m is, 12, and 3n minus 6 now is 18 minus 6 is 12. And so in this graph, m equals 3n minus 6, but we know that it contains k5, a subdivision of k5 as a subgraph, and so this is non-planar. So there you have it. There's conclusive evidence that it is absolutely impossible to tell if we know that the size is 3n minus 6. It's impossible to tell, because here's one that satisfies that that's planar, here's one that satisfies that that's not planar. It could go either way, and there's plenty of other examples, 2 examples like this. All right, let's move on. Still in section 14.1. Now problem 14. Determine all planar complete graphs Kn. All right, so I mentioned that in the last problem. This theorem that says, so let me state a couple things. So I'll say recall, let's say if H is non-planar and H is a subgraph of some other graph G, then certainly, right, so we would get G by adding some vertices and some more edges. Certainly, if we can't make H planar and it's inside of G, how could we possibly make G planar? We can't. So we'd say then G is non-planar. And we also have this theorem that tells us that K5 is non-planar. So with Kn, or let's say K5 is a subgraph of Kn for all n greater than or equal to 5, right? We can find a complete subgraph of order 5 if n is greater than or equal to 5. So what this is telling us is that if n is greater than or equal to 5, K5 will be a subgraph, and then using 1 here, that'll tell us it's non-planar. So Kn is non-planar for all n greater than or equal to 5. And we want to determine all the planar graphs, planar complete graphs, so we know we don't have to check anything with n greater than or equal to 5, and then the other ones we can give a planar embedding. So K4 is planar. We saw that in the last one. Here's a planar drawing of K4, or a planar embedding of K4, looks like that. K3 is certainly planar. I'd have to work hard to draw that with crossings. And K2, I mean, that's just an edge, of course that's planar, and K1 is just a single vertex, of course that's planar. So these 4 are the only complete graphs that are planar. Hint, hint, there's something in the exam that's very similar to this. So hopefully you're watching this video and working on the exam. All right, so that's cool. By the way, that's Kuratowski's theorem, which says that if a graph contains a subdivision of K5 or a subdivision of K33 as a subgraph somewhere inside of it, then it's non-planar, and that's if and only if it's non-planar. That's an amazing theorem. If you keep working hard, and maybe you go to grad school for math, if you're interested in that and you take some graph theory classes, you'll see a proof of that. It's really interesting, and it's probably one of the greatest theorems ever proven in graph theory, in my opinion. It's pretty incredible that that's what it comes down to, is K5 or K33. Absolutely amazing. All right, 14.2, prove or disprove. If G is a graph with an odd cycle for which there exists, so we're on to colorings now, for which there exists a 3 coloring, then chi of G is equal to 3. So I want you to recall a couple things for this one. So recall, if H is a subgraph of G, then if we can color H with K colors, right, if the chromatic number of H, right, remember that the chromatic number of a graph, that's what we use this chi symbol for, chi of H, chi of G. It's the chromatic number, that's the smallest number of colors required in order to give a proper coloring of the graph. So a coloring where any 2 vertices that are adjacent are given different colors. So if the chromatic number of H is some number, then certainly we wouldn't be able to use fewer colors for G. That means the chromatic number only goes up in terms of subgraphs. So if I have a subgraph that's has chromatic number 5, then any graph that contains that would have chromatic number at least 5. Now we also know, so there's one thing we know. Another thing we know is that odd cycles, the chromatic number of any Cn, where n is odd, is equal to 3. That any odd cycle has chromatic number 3. We can't do it with less than 3 colors, right? So let's take an odd cycle, 1, 2, 3, 4, 5. Let me draw the edges here. And I'm just going to use 1, 2, and 3 as my colors. So I know I have to color this 1, and that means this one must be a different color than that. I could use 1 again, and now I could use 2 again. But now, no matter what I did there, I'm going to end up with this last vertex adjacent to one of 1 and one of 2, and so I have to use a third color for that. So this proves any odd cycle, well, it's at least an example, but the same is true for any odd cycle. The same logic can be applied. Any odd cycle has chromatic number 3. I can do it with 3 colors, but I can't do it with 2 colors. So 3 is the smallest K for which there's a K coloring of an odd cycle. So we know those 2 pieces of information. And then notice, so if I have a coloring, so there exists a 3 coloring of my graph. So that means that, so let me write that, since there exists a 3 coloring of G, then, well, I can do it with 3 colors, so I don't have to use more than that. That tells me that chromatic number of G is less than or equal to 3, since I can do it with 3 colors. And then, since G has an odd cycle, contains an odd cycle, well, chromatic number of an odd cycle is 3, and it's a subgraph of my graph G. Hence, chromatic number of G has to be at least 3, because it contains that odd cycle. So together, these 2 things imply that the chromatic number of my graph is 3. Proof. Pretty cool. All right, let's keep moving. Here we're asked to determine the chromatic number of a cube, the cube Q3. So just a quick aside here. Remember how to find cubes. Q1 is the same thing as K2. So that's Q1. Q0 is just a single vertex. Q2 is, it's Q1 cross K2. So I'll have these two, and joined up according to that path. And then Q3, I get, this is a recursive definition for these cubes, cross K2 again. So that means I'm going to take, I'm going to draw my favorite drawing of this thing that happens to be planar, by the way. So there's one version, there's one Q2. Here's another Q2. So there's my 2 copies of Q2 for the K2, and then they're joined up according to K2. So there is one way to draw Q3. And so what we're trying to do is determine the chromatic number of Q3. So one special property of Q3, do you see any odd cycles in it? Remember, if there's an odd cycle in it, we know the chromatic number is at least 3. There are actually no odd cycles in this thing. And in fact, there's no odd cycles. That means it's bipartite. So let's try coloring this. And this is, yeah, hopefully we'll see what's going on here. So I'm going to color this one 1. And that vertex that's colored 1 is adjacent to 3 other vertices. So I got to use different colors for those. I can get away with a greedy coloring here. I'm just going to color those all 2. And then, all right, let's see. This vertex here is adjacent to 2 2s, and so I would have to color that 1 or a third color, but I'm trying to do as few as possible. I would color this one 1, and then this one I would have to color 2. And then look, this last one I have is just adjacent to blue vertices, and so I can color that one 1. So actually what we can see from this is the bipartite, the partite sets. So this graph is bipartite because it's 2 colorable. And the vertices, the red vertices are one partite set. See how there's no adjacencies between the red vertices, and the blue vertices are the other partite set. Notice no adjacencies between those. And so, well, I certainly can't do it. I mean, this coloring, anytime I give a coloring, that gives me an upper bound on the chromatic number. If I can do it with two colors, that means that the chromatic number is less than or equal to 2. But chromatic, a one colorable graph is just a set of isolated vertices. There would have to be no adjacencies, right? Because as soon as I color one vertex, anything it's adjacent to would have to be another color. And so the only graph, this is a theorem in the book, the only graph with chromatic number 1 is just a collection of isolated vertices, which this is not. And so that tells me that chromatic number of Q3 is greater than or equal to 2, and hence chromatic number of Q3 is equal to 2. There we have it. Hence it's bipartite. Okay, ready for the monster problem? I don't know if I am. So here's this monster graph. Remember, right, so this one is going to kind of try to lead us to an answer, but it's not going to turn out to be very helpful. So remember, chromatic number of a complete graph is the order of the graph. So chromatic number of Kn is n. And actually, if the chromatic number is n, if and only if, it's a complete graph. And so if I can find, that's one thing to look for. So like in the exam, you're asked to find a proper coloring of a graph. One thing to look for is, what's the largest complete subgraph inside of your graph? Because that'll give you a lower bound, right? If I know that like K3 is in my graph, then since K3 requires 3 colors to color it, that would tell me that chromatic number of H would be greater than or equal to 3. Or if, let's say, K5 was in my graph, then that would tell me the chromatic number of my graph would be at least 5. So that's one thing to look for a lower bound. But we can look at this graph and see, is there any triangles in here? Is K3? Certainly K2 is a subgraph of every graph, because K2 is just an edge. But do you see any triangles in here? There's not any triangles. And so there's not any K4s or K5s or anything like that. So the largest complete subgraph in here is K2. And this sucks because it gives us a really small lower bound, right? Unless a graph is a collection of isolated vertices, its chromatic number is automatically greater than or equal to 2. And so this is garbage. What does it say about chromatic number of G? It just says the chromatic number of G is greater than or equal to 2, which, like I said, is crap. So it just doesn't help us much. The one on the exam, looking for this complete subgraph, that should help you. It'll give you a lower bound. It'll give you something to shoot for how many colors you might need. This one, on the other hand, it's just tough. It's just a tough one. Finding colorings of graphs is definitely a hard problem. It's technically, it's a hard problem, NP hard. So what we want to do here, so again, things to look for when you're finding colorings, finding the chromatic number of a graph, is, do you know the chromatic number of any graphs that sit inside of your graph? So notice that we have this outside cycle, 1, 2, 3, 4, 5, 6, 7. So my graph contains an odd cycle, which means, I'll write it here, since G contains C7, the chromatic number of G has to be at least 3, because I need 3 colors to color the C7. Now it's actually going to turn out, I'm not going to do a full, completely rigorous argument, but 3 colors does not suffice. We just can't do it with 3. We actually need 4 colors for this. I'll sort of hand wave my way through that argument, but first let me just give you a coloring that works here. So I'm going to start by coloring the odd cycle on the outside. So I'm going to go 1, 2, how about I go 1, 2, 1, 2, and then I'll need my third color for this one. Now this vertex here, I could color that one 1. I could color this one 2. I could color this one 1. This one I could color 2. This one I could color 1. Wow, we're in a really good place. We've only used the third color once. Here, 1 and 3. 1 and 3. I would need to use 2 for this one. And then here, this guy is adjacent to a 1 and a 2. So the hand wavy part here is I'm going to say no matter how you color this outside cycle, and you could run through all the possibilities, we need 3 colors, and no matter how you do it, you're always going to get this situation where one of these vertices in this inner 7 vertices is going to be adjacent to a 1 and a 2. Hence, you're going to have to use color 3. No matter what, you're going to have to use a color, each color for these 7 inner vertices. And what that means then, because this guy is adjacent to each one of those, that I need to use a 4th color for that. I'm going to use this crazy rainbow color. So that's sort of the argument here, is that, so what this shows is that we have a 4 coloring of the graph, so chromatic number is less than or equal to 4. So what this is telling us is that chromatic number of G is between 3 and 4. And so we have to have some argument that says we can't use 3. My argument goes like this: no matter how you color the outside cycle, the inner 7 vertices you'll have to use 3 different colors for those, and we could do that exhaustively, just show any way you do it, you have to have those 3 colors in those inner 7 vertices. And once you have those 3 colors in those inner 7 vertices, then the central vertex here would have to be color 4 because it's adjacent to all of those. So that's the idea here, is that argument would prove that chi of G is greater than or equal to 4. You can't do it with 3 colors, and hence, I'll say verbal argument here. Hence, chromatic number of the graph is equal to 4. So remember, this is important things to remember: look for subgraphs. If you get a coloring of the graph using k colors, you know the chromatic number is at most that. And then if you find some subgraph that requires, I don't know, k colors to do the subgraph, then you know the chromatic number is at least that. And sometimes that's not good enough. Sometimes you need to go a little bit farther, come up with some other argument that says you can't use so many colors for it. But that's the idea. Okay, that's all I have for you here. Boy, I hope you enjoyed the class. Hope you enjoyed this video. That's about all I have for you. Okay, good luck on the exam. See ya.